Okay, so we're going to do a little bit of discussion today about what a spectrophotometer is. We used one earlier in the lab when we used the SpectraViz. It's kind of like a small spectrophotometer. You guys are using, or you're going to watch me use a colorimeter, which is a spectrophotometer only at 4 different wavelengths of light. So anyway, and I'll show you the colorimeter when we actually do that part of the lab. But we'll test 4 different samples of our dilutions, our 0.2, 0.1, 0.05, and 0.025 molar copper 2 nitrate solutions. So what I want to do first is just give you a little description of how the device works. We've already talked about how you select the best wavelength. So if you're looking for blue light, you'll select something that's obviously not blue light. You want to select something that are the other colors of light to see how much blue is actually present. Okay, so a spectrophotometer is actually a machine that measures the concentration of a solution based on its absorbance, how much of that color that it absorbs. Your eyes kind of do the same job, just not as well, but if you look at the Kool-Aid glasses there on the bottom of the screen right here, I would ask you if we were in class, and I'm sure I'm doing that today in classroom, but which one of those is the most concentrated? I'm sure that you would have said the one over here on the right that I've drawn the arrow, that is the most concentrated. Yes, because you see less light traveling through it. And so more of the light is being absorbed. That's because there are more particles in that solution. That would be the one that is the most concentrated. That's how you knew. And so a spectrophotometer, or a colorimeter in our case, essentially do the exact same thing. And so the way it works is it has a light bulb in it, and it shines a beam of pure white light through a sample. If that sample is water, all the light comes through, and it has what we say is 100% transmittance, or zero absorbance. All the light goes through. And so what we'll do each time is we'll blanket. We'll put water in there so the colorimeter knows that the amount of light going through is all of the light. In other words, going through the plastic, some of it's going to be absorbed, but we're going to try to delete that out. And then the spectrum is adjusted just so that you have the wavelength of light that you're looking for. So the way that that works is the white light needs to be separated into its component colors. And I'm sure you've seen it before, and I'll show you a picture in a second. But you can change. The light travels through different media and different speeds. And so if I were to shine light through air, it comes out basically as a white color, and it's got all the colors of the rainbow, and you can't see them separated. But if you run it through, say, a prism, a different type of media like a plastic, or if you use a diffraction grating, which has little bumps on it that allow the light to be separated into its colors, you can then separate it into the entire rainbow spectrum and then rotate or move the prism so that you're only looking at a certain color at a different time. There'll be a small slit that allows the light to travel through, and then you only look at that light through that slit, or that gets through that slit. And the solution absorbs all the colors of light except its own color. That just travels right through. But if you select ones that it absorbs, you could find out how much of it it's absorbing. So here's kind of the way it looks. And I put a link to, a better explanation than what I can do, but, you guys need to see me, I suppose. But anyway, this is the way that it works. So over here is your light source, and your light source sent through a lens. It doesn't necessarily have to, but it would focus the light. And then the light will go either into a prism or to a diffraction grating. So like the glasses that we wore in pre-AP and you put on that separated, so that we could see the bright line spectrum for different elements. It's the same kind of deal, except those aren't prisms. They're like little tiny prisms all over them, but basically they're a diffraction grating. And so what it does is it's separated into component colors, but you saw all the colors. Here, what we're going to do is this slit is going to be moved either up or down, or you could rotate the prism so that you're only looking at a single color that goes through. And what you do on our colorimeters is you select that color that you want to see, and then you shine it through there and find out how much of it got through. How much of it gets through is called the percent transmittance. It's the same thing, just kind of the opposite of absorbance. So absorbance is going to be basically the percentage that's not getting through versus that's getting through. It's how much of that light is actually being absorbed. And then it comes out on a digital reading that you can see. And our colorimeters will be attached to the lab quests that you guys used from last year. And you'll just write down the data. And I'll do that for you tomorrow, and you'll see the data. So how this is all related together is a mathematical formula called Beers-Lambert law or Beer's law. And so Beers-Lambert equation or Beer's law. So it's a mathematical equation that relates that concentration to its absorbance value. And the formula is E equals epsilon BC, which I've got written right here. I usually write it as A equals ABC, where that is your molar absorptivity constant, B is your cuvette length, and C is your concentration, which is what we're looking for. Now, the B cuvette length is almost always a single centimeter, so that value is 1. And so the molar absorptivity constant, that epsilon or the A, if you write it A equals ABC, is basically how the absorbance is related to the concentration. And it's constant for different substances. So there's one for copper 2 nitrate, there's one for iron 3 nitrate, and so forth. But anyway, it is a constant, and you could look it up, or you could calculate what it is if you knew what the concentration of absorbance was. It would just merely be in your absorbance versus concentration. It would be the slope of your line. So there you go. That's Beer's law in essence. So you're going to need to know, this is the molar absorptivity constant, little lower a or epsilon if you like. You'll need to know what those three are and be able to describe them. But basically your absorbance and your concentration are directly proportional. And that's how we're able to figure it out. So relatively speaking, your absorbance and concentration are kind of the same thing. They're just related through the absorptivity constant. Okay, so just a quick little review kind of thing, but a solution that is concentrated contains what dissolved particles? And if I'm really simple about it, I would say it contains many or a high concentration of dissolved particles, right? Or lots for some of you. When light from a spectrophotometer passes through a sample, it will be what by the solution? When light from a spectrophotometer passes through the sample, it will be absorbed or transmitted, but it'll be absorbed by the solution. The more concentrated solution, the absorbance, the higher. More will be absorbed if there are more particles present. So the higher the concentration of particles, the more it's going to absorb. And what would that mean about its molarity? It would also be a larger concentration, so a higher molarity as well. Okay, so that was basically what we wanted to go through with you guys. The absorbance range for your planned solutions, you're not going to be able to discuss it with your partner like we're going to do at school, but you need to figure out what that's going to be. I'm going to select it on the colorimeter. You are, however, in the post-lab questions going to have to decide for some other compounds, having been given some absorbance versus concentration data. But yeah, so there you go. If you have questions, we're going to be available for you guys on Zoom at some point, but when we get closer to it, we'll let you know what it is. Okay? So good luck on day 3 of the lab.